second one is second one is random.
Quick sort. No.
Like checking if the matrix multiplication is correct or not.
So there's well,
Yeah, I think that there's some error on the inequality.
Oh yeah, that should be the other one.
Oh, okay.
Yeah, because it doesn't work.
Yeah, it
And I checked the other one, and you failed the first iteration on the other side. So it makes no sense.
Okay, so you got that down too. The number 2, you got it down.
No, I didn't get it done, but I just know what the problem is. I haven't figured it out.
Yeah, and
We can like discuss it.
yes, please, because I haven't even had a chance to look at it. Just the first one I did it, the second one I read it, but I haven't even tried it. I'm gonna be short of time this time because.
I mean, it's due Monday, so we still have time.
Oh, it's not. They changed it.
Wait,
I thought it was Friday.
Isn't it November 5th?
Yeah, it's Monday. Okay, cool. That's good to know. What's that?
Yes.
But it was there.
I'm assuming it well.
I see what. From where?
I don't know, that's the front desk.
Was there someone there?
No. Somebody goes there very early in the morning. I think that might be happening. Nobody was there, by the way. I just looked and he was there. And I just asked around and got it.
I want to know who did this.
No, it's a big mystery, right?
He did not return for the weekend and now he returns.
Alright, we're gonna get started. So we have very few announcements, or I have very few announcements. See that we have very few students. It must be that time of semester when. Yeah. Anyway, so there's a homework. I hope some of you have seen it. This is entirely theory. There's no programming for this homework, so depending on how you feel about these things, this could be trivial or this could be painful. You know best. So I encourage you to start soon. If it's trivial, get it out of the way. If it's painful, you need the time. So start soon. You know, this is the homework where we will cover pretty much all of the learning theory, back learning, and VC dimensions. So then, usually there are these VC dimension puzzles. Finding VC dimension is basically like solving a puzzle, and this is like a standard template for these things. So I encourage you to get started soon. There's also a question on AdaBoost. The AdaBoost question is at the end, and it's not so much theory, but it's more like the perceptron question in your midterm, where you actually step through the process and just so that you get a sense of what's going on. Has anyone started? Are there any questions? There was some clarification about there was a bug fix, let's say. Yes, there's a question.
Can you describe in detail for question 1? So what are the 2 rules mean exactly? So it seems there. So you have, for example, n parts, and then when you break those up, you have 2 n parts.
You don't choose. You can choose to not break something up. So you don't necessarily have 2 n parts. Do you have a clarification on this?
Question for clarification.
Okay.
If you break apart, you have to use both pieces.
So if you break apart up, okay. So this is. I want you to write down the assumption. That you could. It didn't occur to me that this was an option. Write down your assumption. Either you have to use both, or you have to use one. But I'll get back to you. You had a question. I don't think I got to the end of it.
That was almost my question. So what are the rules exactly? So when you choose.
So the rules are. Now that I realized it, the rules may be a little leave a little thing for ambiguous. So let's say you have n parts, 3 parts here. You can either choose to use the part as is, or you can choose to break it into 2 things, and this gives you 2 pieces. And at this point, the question that came up was, do you have to use both of them, or do you have to use only one of them? And what I suggest is, there are only, I think, 3 possible ways of addressing this. So pick an option, explain how you are analyzing it, and we'll grade it as it's right. There was a question somewhere here. Yeah?
And also, if you break a part up, you can't use the original part, right?
If you break a part up, you can't glue it back together. Yes, you can't use the original part. Yes. Yeah, let's assume that is true. Yeah. Other questions? We'll be done with homework 2 grading soonish. I was hoping end of last week, but I'm hoping end of this week this time. And this time it seems more likely that it will happen. So just hold on, and you'll get your feedback soon. And there were some clarifications or questions about projects, but I'll take project questions on Thursdays at the beginning of Thursdays. Any other logistical things? Any homework questions? Once again, I strongly recommend you start homework too soon, because based on past experience, students have told me that this homework is the one that takes a lot. It's the most difficult one, not necessarily the most time-consuming one, because once you see the answer, it's obvious. All you have to do is write it up. But it takes some time to digest it, and so the learning theory tends to be the one that is slightly difficult for students. So please start soon. We're going to continue with where we left off. And this morning I realized that we are at least a couple of lectures behind what I had hoped for. But that's okay. I mean, I don't need to get to the end of all the lectures. It's more important that we actually get comfortable with what we see. So let's get to boosting. In the last lecture, we saw add a boost and we saw boosting. Boosting was an example of an ensemble method, and it was a rather simple algorithm. It was a constructive proof for a certain question that resolved a certain question that came out of learning theory. The question was, suppose you have a concept that is weakly learnable. In other words, suppose you have a concept where you have a learning algorithm that can always produce a classifier that is slightly better than chance. Is the concept strongly learnable in the PAC sense? It's a theory question. And it could have had an answer that is, just a proof that says, yeah, it is learnable because of this mathematical argument. It turns out the answer to that question, the way the question was resolved was not just by argument, but by construction. By showing an algorithm and saying, here's an algorithm that can take any weak learner that you have and boost it into becoming a strong back algorithm. And so it's a rather simple algorithm. It's really fast. All you have to do is I give one more additional parameter and call the weak learner those many number of times. It's fairly simple to implement except for this one conceptual thing involving the weak learner. Yes?
Sorry. So when we were talking about weak learners, is there any like range of like accuracy percentage?
Yes. It goes back to the theorem. By weak learner, we mean that it should always produce a classifier that is better than chance.
Better than chance, but not too complex, meaning.
Oh, that's a vague argument.
Okay.
It's not too complex. It just means it's like a VC dimension kind of an argument. You don't want the weak learner to be to have a high VC dimension because boosting increases the VC dimension, and as a result, your models can become over complex. So that's not a rigorous statement. That's more of just it's a statement about complexity. You should always remember that you want it to be, you want your weak learners to be weak in some sense, from the expressiveness point of view. So you can use this method with any weak learning algorithm. There is one caveat, namely, your weak learner, you can't just take, for example, the decision trees that you may have implemented and plug it into this directly. You need to slightly re. At the heart of this was we needed an algorithm that could respect some sort of a distribution over the examples. Because we maintain this at every round, we have this thing that we state that we maintain called dt, we call it the distribution. It essentially said how important is each example. And we want a learning algorithm that respects it. But the learning algorithm doesn't have to be really complex. All you need is to find a model tree, for example, that is better than chance. Now, caveat is that this performance of this one depends on the weak learners that you use. And as I said, if you use a very complex weak learner, it could end up hurting us because the final hypothesis that boosting constructs is a more complex thing than any weak learner that you use. So you are actually adding complexity, and we know that complexity is a bad thing. Anyway, so one interesting point that I ended the last lecture with was this really cool paper by Rich Caruana and this line of work, which pointed out that if you have a small number of features, by small at that time, this was 2006, it was about 300 features or so. Probably one of the best things you can do is to use boosted decision trees. It's a good black box classifier. It's just something that you can throw at your data to see what happens, and it tends to be reasonably good and tends to outperform other methods for that class of problems. One clarification I wanted to mention was regarding this curve that I showed in the last lecture. The blue line, the line at the bottom, this one here, is the training accuracy. The theorem from AdaBoost tells us that the training accuracy exponentially goes down and goes to 0 very quickly. And empirically, the observation was, so what we expect is as the training error, as the number of rounds keeps increasing, we are adding more and more weak classifiers, so we may end up overfitting the data. So we expect the test error to go up, and I mentioned that there's this strange observation that the test error really doesn't go up, it stays flat, and the way I left it, I made it sound like this is a great mystery. It turns out that's not a great mystery. I don't want to leave you feeling that anything is a mystery. There's no magic to machine learning. There are actually rather clean explanations for this that involve the margin of the higher order classifier that we built, and so I just wanted to clarify. Okay, so any questions about boosting before we continue with ensemble and beyond?
Yes, I just didn't understand that last part. So why is it that it stays the same?
Oh, why is it that? Okay, so this is a slightly more complicated answer that's going to take longer. The simple answer is that adding more and more weak classifiers increases the dimensionality, right? So dimensionality goes up. When the dimensionality goes up, we know that the VC dimension goes up. So let's write it out. VC dimension goes up. So as P, why can't I write P in? As P increases, VC dimension increases. Now, this paper here showed that as P increases, see again, as P increases, the margin of the linear classifier that we are developing also increases. And it turns out if the margin increases, the VC dimension decreases. And we will get to that maybe in another 20 minutes. So these two things seem to balance each other out. And this is a very subtle argument that required a few assumptions, which is why I'm a bit uncomfortable going through the whole detail. But this is the rough argument here. Okay. Yes. Did you have a question? No. Okay. So now we're going to just very briefly look at other ensemble methods. Ensemble methods are one of the most important things methods that you should be aware of. It turns out that very often the ensembles are just committees of classifiers. Instead of using one classifier, you have a whole bunch of them, and they somehow make it come up with a consensus decision that that seems to be better. Ensembles are an important tool that you should use. You should always think about. If you are doing research in machine learning, building an ensemble does not make the paper look fancy because everyone agrees that ensembles work. But if you're using machine learning in applications, you should always think about an ensemble because everyone knows they kind of work. So I'm going to cover 3 different algorithms for ensembles, but this is going to be super quick because frankly it's rather easy. In general though, like I said, an ensemble is a general class of methods that use other classifiers and combine the output, and they tend to be empirically robust. It used to be the case that when I mentioned the Netflix challenge, people knew about it, but maybe it's been a while. So in 2008 and 9, Netflix organized this challenge called the Netflix Prize. It offered $1 million to the team or the person who built a model that could predict user ratings better than anyone else. And they provided a ton of data. And it's kind of telling that the team that won the Netflix challenge, the name of the team was the Ensembles. It was an ensemble of classifiers produced by 2 different teams. They kind of merged. And each of those were themselves ensembles. They got $1 million. It was ugly. It's not something you can write a paper about. It's not elegant, but it worked. So, boosting is an example of an ensemble. It has 3 stages, if you think about it. There's an initialization stage where you weigh all training examples equally, and then you iterate. At each iteration, you call the underlying model that you have. You train a model on the weighted training set. You compute the weighted error, and you promote examples which were difficult, and you demote examples which were easy, and you keep building this. And it usually requires a few hundreds of iterations. This is just a rule of thumb. It's not. There's no theory there. At the end of this process, you return the final model. The final model has to, for any ensemble, the final model has to somehow combine the outputs of all these classifiers that are there. And at a boost, the final model is a carefully weighted combination, and the weighting is chosen by how correct or how good each of these weak classifiers were. This is just an example of an ensemble. There are many different perspectives about boosting. I mentioned that boosting can be seen as something that maximizes the margin. There is another perspective that compares boosting to logistic regression. You know, if you have this really cool thing that works and different people analyze it from different perspectives, and it seems like boosting has something to add a boost at least, has something to offer to every kind of an analyst. So it keeps people who like math quite busy. It's a linear classifier at the end of it. It's a linear classifier where you can think of the weak rules of thumb as feature transformations, but the feature transformations themselves are learned. So there are different perspectives. There's a lot of literature on boosting. You can find me afterwards if you want to read about this. Let me move from boosting to another ensemble method called bagging. Bagging is short for bootstrap aggregation or bootstrap aggregating. Leo Breiman is responsible for this, and it's a rather simple process. Okay? Imagine that you have a learning algorithm, any learning algorithm, pick a decision tree or a perceptron or anything. You're given some training examples. You repeat some process multiple times. What you do is at each step, you sample some number of examples with replacement. So you have a big bag of examples. You draw an example, keep it aside, you keep note of it, put it back in the bag, keep drawing this. You sample examples with replacement. This kind of sampling is called bootstrapping, bootstrap aggregation. And then you have now a sample of examples, a subset of examples. You train your classifier on whatever learning algorithm. And then you do this many, many times. I say m here and m here. Imagine that this is some other number. It could be a hyperparameter. You draw a certain number of examples with replacement. You train a classifier. You do this many times. You get many classifiers. The final classifier is simply the voted. So the final classifier is simply the one where all these underlying classifiers vote on the answer. It's so simple. You should be able to implement this because all you need is some learning algorithm. There's no need to modify your existing learning algorithm. You just take whatever you have and do this process. Does it make sense? Any questions? I've heard your voice a lot. I don't think I've heard your voice, so I'm going to go to you first.
So what if you choose the same set of examples every time?
You can. This is the power of randomness. It's fine. Bootstrapping is a way of essentially amplifying your data, and it works. And it comes with, if you read the work of Breiman, you'll see that this actually has interesting statistical guarantees. So it doesn't matter. That's the point.
Just m prime, is consistent or is it not consistent between each iteration? Like
It's the same number. Pick up a number. So this algorithm requires m prime as an input and t and a learning algorithm, and it produces a collection of classifiers. Other questions? Yes.
So these votes, they're not weighted at all?
No.
Like,
No, and that's the reason. They're not weighted, but because some examples may be oversampled, that implicitly provides some sort of a weighting. So it's a method for generating, multiple versions of a predictor. So you have, imagine that you have a learning algorithm that produces a model, like a decision tree if you want, and there is this gold standard decision tree that produced the data. But you only have a subset of it. I'll get to you in a minute. You only have a subset of the data, of all the data that is possible, and you need to make do with that. Instead of generating one tree using the data, you generate multiple possible trees, multiple possible classifiers, with the hope that, good trees or trees that look like the right tree will show up more often. And so, the right prediction gets more votes. Yes?
Does the algorithm have to be the same for every classifier?
Yes, that's right. So you're given a learning algorithm. But in fact, that's an interesting point. In theory, there's nothing that prevents ensembling a diverse collection of algorithms. So you can use this for classification. You can use this for regression. If you're doing classification, every classifier votes for the on the label, and you take the label that has the highest number of votes. If you're doing regression, every classifier predicts a real number, and you take the average, and that's it. So these multiple versions of the data set are called bootstrap replicates. And what you do is you create, loosely speaking, you create bootstrap replicates of the data and train classifiers on each of these things and aggregate them. That's why it's called bootstrap aggregation. It turns out that bagging can actually give substantial gains in accuracy, and it also has some interesting statistical properties. But I'm not going to get into the details of the statistical properties of bagging. If you're interested, I can point you to some tutorials on this that actually go into this. There is, in general, basically the idea is that if you slightly perturb a data set, if your classifier changes drastically, then bagging can give good improvements because you get a diverse collection of classifiers that vote on it. Just as an example of bag decision trees, this is an example of bag decision trees used for regression. So imagine that every tree is a regression tree, meaning the leaves are actually real numbers, or leaves somehow produce real numbers. You draw T bootstrap samples, you train the decision trees, you get T trees, something like this. And when a new example comes in at prediction time, each of these trees produces a number, all of these things, and you average them. And that's your answer. So, one thing that you should always ask yourself is when you see any new learning technique, there are a few things you should ask yourself. One is, what's the learning algorithm? In bagging, the learning algorithm is you draw bootstrap replicates and you train something. Two, how do you make a prediction? How do you make a prediction? Here, each of these trees predict and you average it. The third one is, does this work? Why does this work? And that's the theory of it. You're not going to get into the theory of bagging, but it has some theory. And the fourth one is, what assumptions does it make? What hyperparameters does it use? In bagging, you need to give it a couple of numbers, a number of bootstrap samples that you need to take, and the size of each sample, the M prime from the, yes?
So we could literally do this, the T times and never hit a particular example.
Yeah.
But it's more accurate.
No, there's no guarantee that it's more accurate. It's more stable.
More stable.
Yes. There's no. Of course, yes. In fact, that's a good observation. If you do this process, there is a certain probability that you will never see a particular example. As a result, you may actually get a classifier that's suboptimal. All your classifiers are suboptimal, but interestingly, there are some guarantees that show that if you do this enough number of times, you will hit everything, and the probability that you will not get an example is going down, so you will get a stable enough classifier. Yes.
So earlier you said that Amazon or Netflix winner was using a large ensemble. Is a large ensemble just a large T?
Yeah. Well, it was not bagging. I don't remember what their ensemble was, but it was a large T for sure. And it turns out their local models are also fairly complex. Yeah.
So, can we think each of those M prime as a subset of the training set?
It's not exactly a subset because you take examples with replacement. So it's not a subset because the same example may be drawn again. So some examples may show up multiple times.
Okay, so they can the same value can occur in different subsets.
Yes, that also.
Oh, yes. But will that affect our the votes because it's occurs multiple times?
It works. It does not matter. Random forests are really bagging plus plus if you want. There's only one change. You draw multiple bootstrap samples, and you also draw subsamples of the features. You don't use all features for every tree. So if you have, say, 1,000 examples, let me not use 1,000 because that's already. Let's say you have 500 examples. You produce a bootstrap sample of some size. Let's say you produce a sample of size 100. And let's say you also have 20 features in your task. You subsample that somehow. You need to decide how many features to sample in each round. Let's say you take only 10 features. And using these 10 features for this 100 examples, you train your classifier. And random forest, as the name suggests, uses decision trees. So you train a decision tree, and once again, the final prediction is the average prediction. Now, this adds to the robustness a bit more. Random forest tends to work surprisingly well, and if the idea of dropping features makes you uncomfortable, we will revisit that when it turns out in neural networks again. One of the most popular ways of making neural networks stable is called dropout, where you essentially randomly drop features. And it leads to more stability. There are connections to generalization, formal connections between that and generalization. Yes?
So just for clarification, when you're picking your features, I guess I'm a little confused. So you do all your samples, all your bootstrap samples, and then out of the samples you put everything on features that you're splitting on?
Yeah.
And it's the same for all of them though? Like all
For
of them.
that particular bootstrap sample. Given a bootstrap sample, you have a feature set.
So a different sample
Might use different features.
might use different features.
That's right. That's right. Yes.
Do we get stability because we're doing replacement? Because I imagine even with the big data set, if you were to do just subsets, that it could be more stable.
Yeah, so the sampling with replacement actually gives us, allows us to do the theory. You could actually just do this without replacement. It would work. So that's the nice thing about ensembles. It's shockingly robust to these kinds of tweaks. For example, in fact, if you think about it, boosting also does some sort of sampling of the training set. You sample the training set, but you don't do a real sample by keeping numbers. You keep it, you upweight and downweight. So some examples essentially show up more than once. It shows up 1.5 times because it's weighted more, for example. So in some sense, sampling with replacement allows you to increase the importance of a certain region of the instance space. And suddenly you get an expert on that region of the instance space. And then you get little experts on multiple regions of the instance space, and then they all aggregate together.
So why is it called bootstrap? So
I don't know why it's called bootstrap.
So, no, according to my understanding, bootstrap means literally you should be trying to lift yourself.
Oh, so it turns out that the word bootstrap is has multiple meanings even within machine learning.
So say the algorithms or the heuristics that Alan realized.
That's a different bootstrapping.
Yeah, but it makes sense to be a bootstrapping.
Yes.
Each iteration is not really making a knowable improvement. So
no, I honestly don't know why it's called bootstrap. It has some. I don't want to take a guess. I don't know. I don't know why it's called the bootstrap. You should look it up. I would be curious to know. Yes.
Is there any reason why it needs to be decision trees or?
No, well, it's called random forest, so you have trees. You could do this with other things. Yeah. Yes.
So you have been doing average prediction on the trees, but if we have like Boolean outcomes when we do like a mode,
You do the mode. Yeah, you take the mode. Yeah, basically, if it's multi-class, you take plurality. If it's binary, you take the mode. Yeah. For regression, it's the mean. For classification, it's the mode. So that's pretty much all I have to say about ensembles, really. It's, it's a large class of methods, but essentially it gets repetitive after a point. General idea is you construct a way of generating multiple classifiers, each of which may be have the opportunity to be slightly different from each other, and you aggregate all of them. What you need to know is, so it turns out boosting is just an ensemble method. It comes with some rather interesting guarantees, and it has its lineage in learning theory, but the other kinds of ensembles like bagging, etc., have their lineage in statistics. They are fairly robust. You need to know what AdaBoost. You need to be, at least, I won't ask you to implement AdaBoost, but you should be in a position to implement it if necessary, and you need to think about what you need to change in your learning algorithms to implement it. You need to be able to implement boosting, bagging and random forests, because that should not be terribly complicated. And now you have a whole bunch of methods to layer on top of any learning algorithm that you have. Because if you have perceptron, you can have bagging on top of perceptron. If you have random, you have decision trees, you can do random forests on top of it, and this gives you a whole bunch of things to try for your project, for example. Any questions? Yes?
Why is it specifically random forest? You can just bag pretty much any.
You could. It sounds like a nice name. It's just a name. That was the same question that came up before. You could apply that idea of taking bootstrap samples and subset of features to train any classifier and doing that many times. If you do it for trees, it's called random forest. Alright, so now we're going to do something completely different. I was hoping to get to this at the beginning of this lecture, but ensembles didn't finish. So we're going to look at support vector machines. And just to make sure we kind of know where we are, we've seen a few learning algorithms. We've seen decision trees, we've seen perceptrons, we've seen AdaBoost, and generally ensembles. We've also seen linear regression. And perceptron and AdaBoost both produce linear classifiers. Sure, AdaBoost produces linear classifiers on top of the weak hypotheses, but imagine that every weak hypothesis is a feature. Like if every feature was a weak classifier, then AdaBoost is basically a linear classifier. And actually there is, like I said, AdaBoost has a lot of different kinds of analyses. One particular analysis of AdaBoost involves comparing it with something like perceptron. Anyway, we've also seen a whole bunch of general principles of machine learning. We've looked at the idea of overfitting. You should be aware of it and you should beware it. We've looked at mistake-bound learning and back learning, sample complexity. Hopefully you're comfortable with the idea that the choice of your hypothesis makes a big difference. If you choose the right hypothesis, you can actually learn. If you choose a very complex hypothesis that contains what you need to learn, search might become really difficult. And one way of measuring the complexity of hypothesis is using VC dimensions. And that seems to work fairly well. Still kind of does not for neural networks, but kind of does. There is, you must be comfortable with the idea of training and generalization error. Training error is what we can measure on the training set. Generalization error is what we truly care about, because that's what we want to keep low. Coming up, we're going to see how, as a direct result of certain results, certain observations that came up from learning theory, we can now create a whole new class of learning algorithms, one of which is support vector machines, but a whole bunch of them show up, and this forms the basis of pretty much most of modern machine learning, I would say, namely the risk minimization principle. We've already seen the idea of minimizing loss, And this, we can actually, what we will do now is to justify this more formally. The big picture is, at least for support vector machines, is we know everything about linear models. We know what they are. We know what they represent. We can ask how good is a learning algorithm. I can answer this question in many, many ways. If you answer this using online learning, you get algorithms like perceptron. We've not seen the algorithm called Winnow. It's something that I actually really wish I could spend some time on, but it's kind of fun. There are some slides on the class website on the Winnow algorithm. If you're interested, take a look. We can ask how good is learning, and we can answer it with the pack style of analysis using agnostic learning, and combining this with linear models gives us support vector machines. We can ask the same question, how good is learning, and come up with a Bayesian answer, and combining that with linear models gives us logistic regression. And we'll get to that maybe hopefully in a few weeks. So this lecture is about support vector machines, and I'm extremely ambitious here in listing these 4 things. There is no way I'll get to the end of this. In fact, there's some possibility that I might even have to skip kernels and move it to the end of the semester in the interest of time and in the interest of covering some material on neural networks. I'm going to talk about how we can invent a new training criterion for learning by framing it as a problem of maximizing the margin. Once we write down this problem, formally, it gives us what's called the support vector machine objective, which is an optimization problem. You can, once you write your, and when I say optimization problem, I mean a continuous optimization problem, which is a kind of problem that, convex optimization people have been studying for decades. Once you write a problem as an optimization problem, you get an entire cottage industry of people to work on it. And that's what happens. It turns out, for this particular optimization problem, there's a very cool way of solving it that involves gradients, and we'll get to that. And in the end, we'll see a learning algorithm for support vector machines that is, I think, about 12 characters different from your perceptron in code. So if you've written your perceptron and you are fairly proud of it, keep it. All you have to do is make minor edits and you get SVM. And hopefully we'll get there, and that's something that I definitely want to cover, and if we have time, we'll get to cover. So let's look at this question of training by maximizing the margin. I'm going to go back to VC dimensions. What we know from our learning theory is that if you have M training examples, with high probability, you will get. It's possible to get a classifier that has low error, or rather, if you with high probability, the error of a hypothesis, the generalization error of the hypothesis, is no more than the training error by some term. If you have a hypothesis that has a training error of error S, then your generalization error is going to be that quantity plus a bit more, but no more than that. Now, of course, that bit more could be more than 1, which completely renders this point useless, but you have this thing. Now, what do I care about? I care about minimizing this quantity. I don't care about the training error. I can make it 0 if I want. I'll just remember the training set, and that gives me 0 training error. I don't care about minimizing the training error. I want to minimize the generalization error. In order to do that, one way of doing that is to, push the sum of these things down. If I can push the sum of the right-hand side down, everything, the training error will also go down, right? So, what does that mean? What does it mean to push the sum of those things down? We know how we can find a classifier that has 0 training error. Suggests that there should be another term that we should be minimizing. In addition to the training error, there's this other term that gives us generalization. So the general philosophy here is that it's not enough to just minimize the training error. What you need to do is minimize training error plus something else, and that something else will take care of generalization, and you have this trade-off. If you focus too much on the training error, you get overfitting. If you focus too much on the other ugly term, you get overgeneralization, if there's such a thing. How do you generalize? We don't have to think too far, you don't have to be too complicated about it. In order to generalize, given a collection of training examples, without any, if you don't get to control anything else, you reduce the VC dimension. If you reduce the VC dimension, you generalize. So what we need is a training procedure that simultaneously increases the training error and reduces the VC dimension. So far so good? Okay. We also know that the VC dimension of linear classifiers in D dimensions is D plus 1. So we have a problem. I want to reduce the VC dimension. I have these many features, D features, but the VC dimension is fixed. It's a constant. Given the dimensionality, this is a constant. How do I adaptively control for it? This seemed like a problem until we realized that the second statement here is not quite right. It's rather loose, and this was we need to think about whether all linear classifiers in D dimensions are the same. Let's think about this. Suppose, and in order to think about this, we need to bring in the margin. Remember margin that we saw from Perceptron? Margin is going to be a big player in SVM. In fact, another name for support vector machines is maximum margin classifiers. So we have a data set like this thing here, pluses and minuses, and say we have a hyperplane. The margin is the distance from the hyperplane to the data point nearest to it. So in this case, this is the margin of this classifier. You've seen this for perceptron, so I'm not going to spend too much time agonizing about this. But what I do have is a question for you. Say you're given a data set, and I give you two classifiers, H1 and H2. Both of them get 0 training error. And if you had to pick one, which one would you pick and why? Yes?
I think the one on the bottom, because there's a greater distance between all the points, noise is less likely to affect.
H2. Right? You pick the one with the bigger margin. Anyone wants to vote for H1? Or has?
H2 is not correct either. So your margin could be bigger than this.
You
Could be
could be
larger.
bigger, but let's say these are the only two you get to pick from. There is an art, yes.
Do we care about problem-specific complications? Like it's much worse to choose a negative option.
It's literally this data set and these two examples.
What if there were more plus points on the right side? I mean, on each one.
On the right side, who's right? This way, here, right?
Yeah, like
Okay.
I guess if there was like only one minus point on the left side, then the margin wouldn't really matter as much.
Oh yeah, sure. Fair enough, but there's just one. This is the data we have. Given a particular data set, I'm not going to label this one. The answer came up. That was the first one. Really, picking a larger margin is a safer choice because you can get. Let's say there's a new example from that's not from the training set. The positive examples has more room to move around and without forcing the classifier to be wrong. The negative examples has more room to move around without. You have this much room to place negative examples before it crosses the threshold, and so having this margin of safety is a good thing. Same thing here. Whereas here, just a positive example, the same example here, would have caused an error. So there is more room for new examples to live if you have a larger margin. This is just a hand-wavy argument, but I want you to understand the philosophy here first. Yes?
So for this example, we have more like negative sign here. So, but for the H1, we have like more room for negative sign.
Sure,
So.
but we don't know upfront which one is going to dominate. Yeah, in H1 you get more room for the negatives. If you believe for some reason that your new examples are more likely to be negative, you probably want to leave more room there. Yeah?
Or if like having a negative misclassified would be
more dangerous.
That's right. That's right. If you have a higher cost associated with one of these misclassifications, in that case, you want the classifier to be skewed a bit. Otherwise, in the absence of any information, the best thing to do is to put it right in the middle. Intuitively, a larger margin is better, but how do we formalize this? The way to formalize this is to define this idea of a data-dependent VC dimension. Remember, the VC dimension is just a property of a set of functions, right? It's a property of a set of functions. It's asking how many points can this set of functions shadow? I can define a set however I want. Let me define a set. Say you have two values of margin, gamma 1 and gamma 2. H1 is the set of all linear classifiers that classify this particular linearly separable data set with gamma 1. It's a set of functions, right? H2 is another set of all linear classifiers that classify this particular data set with a margin gamma 2. It's another set of functions. And let's say gamma 1 is bigger. Then the intuition is that all functions that have a larger margin, given that both these sets of functions perfectly classify the data set, it is better to prefer functions from H1 than H2. Why? Because all functions in H1 have a larger margin than functions in H2. So there is a bigger margin of safety. This is the intuitive argument. This suggests that even within the set of all functions that perfectly classify a data set, there's some reason to pick one function over the other. You pick functions that have larger margins. You pick classifiers that have larger margins because you need to, there's this intuitive argument. But the VC dimension did not seem to capture it until Vapnik came along. This theorem from Vapnik basically set things straight. Suppose you have a set of linear classifiers that separate a training set with a certain margin. Yeah. Then the VC dimension of this set of classifiers is not d plus 1. It's not just d plus 1. It's the minimum of r square over gamma square and d plus 1. Gamma is the margin and r is the size of the ball that contains all the data. This r square over gamma square must look awfully familiar. It's from the perceptron ball. It turns out this is a fundamental property of this is the r square over gamma square is this fundamental sort of ratio that keeps coming up when you are playing with linear classifiers. It's a complexity parameter, it turns out. So what this theorem says really is that the VC dimension is not just less than d plus 1, it's less than d plus 1 and also less than r square over gamma square plus 1. Which means that if you have a classifier that has an extremely large margin, gamma is going to be huge, r square over gamma square is small, VC dimension gets small. This is why, this theorem is basically the reason why having that intuition basically works. Larger margins give you better generalization. Why? Because larger margins have lower VC dimensions. Larger margins imply lower VC dimension. Lower VC dimension implies better generalization. Questions before we use this idea?
Could you also reduce the VC dimension by getting rid of attributes that don't necessarily have any predictive value?
How do you know that?
You would have to find them by doing folding or...
So that's a perfectly reasonable idea. Computationally that becomes very complicated. Because if you have the attributes, you need to enumerate all possible subsets of them. So you have an exponential number of subsets of attributes to try out. I'm not saying that this is not tried. People do this. There is I can strongly recommend the 2003 special issue of the Journal of Machine Learning Research, JMLR, which completely dealt with feature selection. the introduction to that is awesome. Because at the end of that introduction, you will realize that, yeah, we really don't know what we're doing. Because we have the worst case, the complexity is exponential. You have to try out all possible subsets, and you can't do it, so there are all these greedy mechanisms for doing that. But in some sense, that's what they achieve. Feature selection is an extremely important thing. And frankly, we just play it by ear. Alright, so what we have here is a data-dependent VC dimension that says lower margins give you better generalization, and that gives us a very clean learning strategy. Find a linear separator that maximizes the margin. That's the goal. That's the goal that we are going to try to solve, and that's solving this. Finding a linear separator by maximizing the margin gives us a support vector machine. It's a fancy name. It's just a linear classifier. So that's our agenda for the next half an hour now, and I'm going to build it up to define the support vector machine objective. Alright, so we're going to go back to this the geometry again. A linear classifier makes a prediction by looking at the sign of the dot product of the weights and the features, adding a bias, and if that thing is positive, let's call that thing the score. This thing here. If that thing is positive, the score is positive, then you say positive, not you say negative. You can also measure the distance from the line or the hyperplane to any point. This is what you do in 2 dimensions. In d dimensions, it very cleanly generalizes. Or I could have even written y times b plus w transpose x divided by the norm of w. These two things are identical. And we have a line in d dimensions. This becomes b plus w transpose x equals 0. I'm keeping the b around. Very quickly I'll lose it. Okay? So you've seen all of this. Now, of course, we only care about the sign of the prediction. We don't care about the magnitude, and we're going to use that idea. We're going to use that point. In particular, when I say we don't care about the magnitude, this could have been b plus w1 x1 plus w2 x2 equals 0, or you could multiply everything by 1,000, and the sign of that quantity would be the same. You can multiply it by any positive number, and the sign of that quantity would be the same. Right? The actual value of the score does not matter, only the sign does. And that observation is going to be crucial for constructing the SVM objective. So let's write down the margin in a formal way. I've been talking about the margin as just this intuitive thing. It's the distance of the closest point. Let's write it down in math. The distance of a point from a line is this thing here. It's that, the distance of a point is absolute value of w transpose xi plus b divided by the norm of w. For positive examples, this is positive. For negative examples, this is negative. Which means if I multiply y with this quantity, it's always positive. So you get the absolute value. So the distance of xi comma yi from the line is this thing. And the margin is the distance of the closest point, which means you need to enumerate all the training examples, xi, yi, find the minimum, and that gives you the margin. So it's the smallest element in the set. What we want is to find a weight vector, w, that maximizes this margin. We want to find a w such that even the smallest distance, the minimum, is large, as large as possible. So we want to learn w by maximizing gamma. So this gamma is really a function of w, so I can put this gamma w. In the literature, this quantity is called the geometric margin, the actual distance. If you just look at the numerator of this thing, what I call the score, it's called the functional margin. This thing on top is called the functional margin. Okay? These are just names. I don't care these ones. So far, so good. This is the goal. We're going to try to find a W that maximizes gamma W. And keep in mind that if I change W, gamma W will change because it changes the parameters and it's basically a different line. And B also, this is W and B because I always forget, which is why I recommend you don't, maybe you won't forget. In order to maximize this quantity, we're going to use the observation that we only care about the sign of the dot product and not the magnitude. In particular, this line could have been B plus W1 1 plus. This is the line, or it could have been B divided by, let's say, I'm going to have some number, some B plus 1 plus. That doesn't matter. In general, I can put multiplied by any positive constant. Let's call that constant C, and B plus C times W1 plus B times C1 plus C times W2 x2. And I can take the sign of this. It's going to be the same as the sign of this, as long as C is positive. Now, let me use a very specific choice of that value C, of that constant. I should not have used C now because I'm going to use C later on. But let's say that C is different. But limit enough. Let's call it K for the constant. Now I'm going to use a very specific value of K. Suppose K equals, instead of using just a number, what I will do is I will pretend that I have the true classifier. Imagine I had the true classifier. If I had the true classifier, I could compute this quantity for all of them. Right? If I had the true classifier. I don't have it, but I conceptually could think about it. And I could compute that numerator, and I could also find the smallest among all of those things. It's a constant because I have the true classifier in this hypothetical world. So I want to say that K is the smallest of absolute value of B plus, let's say the true classifier is W star. 1, 1, capital B star, W. Among all X, Y, among all the points. Imagine that I had this, I could calculate this value, right? And if because I have the true classifier, this is just a number, just like the number 2 then. It's a K. If I had that, then life becomes extremely simple. Oh, sorry, this is not the smallest, it's 1 divided by this. Smallest of, oh man, this is a mess. The smallest of 1 over this quantity. This is a very specific choice that I'm making. It's not like I'm just trying out all things and coming up with this. It's going to make our life a lot simpler. We have to just go through some ugly math. But if we had this thing, then for the smallest one, the numerator would cancel out this thing here. Right? We would be left with just the number 1 divided by root of square plus W2 square. Right? For everything else, the numerator would be bigger. But for the smallest one, this would cancel out. So, we have the freedom to scale up and down W however we want, and I'm going to choose to scale it up or down by that quantity there. I'm going to by what I just described here, so that just for the closest point alone, not for the other things, just for the closest point on both sides, the margin is 1 over the norm of W. I can choose to do that because I still don't know what my W is. I can just scale my W however I want. I'm choosing to scale it this way, right? And this does not change the final prediction because it's just multiplying by a positive number. Questions before we run with this idea? Yep.
So if you lock in that choice, does that mean that the square root or the norm of W that you're left with is the best classifier?
The norm of W that you're left with is not exactly the best classifier, but 1 over the norm of W is the margin.
Okay.
Because 1 over the norm of W is exactly that thing. In fact, that's what we're going to do. We want to maximize the margin, meaning we want to maximize the smallest of all these things, but that thing is just ugly. Let's not deal with it. Instead, we use the fact that we have this degree of freedom to scale things up and down, and we change it so that we have to maximize this quantity instead. Nothing has changed because the sign of the prediction is all that matters. The magnitude does not matter. So, we cared about maximizing gamma, but we really only care about the sign of this thing. Instead, we're going to maximize 1 over the norm of W, but now we can't freely maximize 1 over norm of W. We can maximize 1 over norm of W if and only if the closest point has a margin of this, if and only if the small, you get for every point, let me write it. You can maximize 1 over norm of W if and only if the score associated with every point is at least 1. Because the closest point needs a score of 1, because that's how we set the numerator to be 1. Right? If and only if this quantity up there, which I should not be jumping with my back, but SVM is fun. If that quantity up there is 1 for the closest point, and it's more than 1 for everything else by definition of closest. So in this setting, so this is where the functional margin comes in, what the quantity that I call score. Maximizing the margin is equivalent to maximizing 1 over norm of W if the score of the closest point was 1. And only in that case. So we have now a constrained optimization problem. I want to maximize the norm of W, but maximize 1 over the norm of W, but this 1 over is just, let's get rid of this 1 over business. It's exactly the same as minimizing the norm of W, which is exactly the same as minimizing the norm of W squared. Right? Norm is a positive number, and so we want to minimize the norm of W such that for every point YW transpose X is at least 1. If for every point it's at least 1, then for the closest point it is 1. Just that's the definition of minimum. So this gives us a learning problem. Minimizing half W transpose, I put a half there because when we take gradients, things get easier. But you can, if that makes you uncomfortable, you can pretend it's not there. We want to minimize half the squared norm of W such that for every point, YW transpose X is at least 1. Minimizing the norm of W gives us, is equivalent to maximizing 1 over norm of W. Maximizing 1 over norm of W in this setting maximizes the margin. Maximizing the margin in this setting reduces the VC dimension, which gives us generalization. So the optimization problem is totally geared towards maximizing generalization. The condition is true for every example, and especially it's true for that one example that's closest to the separator that we use to construct that multiplier. Questions? At this point, at least one of you is confused. Yes?
So you have to go through and find the point that is closest to the line first before you can apply this, right?
In a hypothetical world, that is what you have had. Alternatively, we can say, for the point that's closest to the line, this property is true. Maximizing the margin is equivalent to this quantity, this thing. But I do want to find the thing that maximizes the margin. So let me just solve this problem. I solved both these things in one chart. This is a property of this. Let's say the solution to this thing is W star. at W star, the property that I described holds. So by solving this problem, not only do I get the W star, but I've also satisfied that condition. It's a chicken and egg thing that you solve. Well, it's not a chicken and egg thing. It's something that you get in one shot. You solve both problems in one shot. Yes?
Is this similar to thinking about how we apply regularization to other kinds of algorithms? You know, we're trying to minimize.
It is. Though I don't remember if I ever mentioned regularization in this class, but it is. It is exactly a regularizer. In fact, this is the VC dimension explanation for the squared norm regularizer. We'll get to that hopefully next lecture. This problem, this optimization problem, is called the hard support vector machine. It's not called the hard support vector machine because it's difficult. It's called a hard SVM because this assumes that we have a linearly separable data set. We'll look at how to solve this problem later on in the next lecture. Today, I just want to talk about stating the problem. This is, in some sense, a nice thing about framing machine learning as optimization. You can separate out the declaration of the optimization that you want to have from the process that solves it. Today, I could use one algorithm to solve this optimization problem, and tomorrow I could use something else, and it kind of separates out this statement of the problem from the solution of the problem. So today, we've just stated the problem. Now, hard SVM, as nice as it is has a problem. It only works when the data set is linearly separable. Let's think about what happens if the data set is not linearly separable. If the data set is not linearly separable, what does it mean when a data set is not linearly separable? It means there is no W such that y W transpose x is greater than 0. This is the definition of linear separability. Right? We saw this for perceptron, for example. For there is no, that's that, for all xi, yi. Oh, sorry, not greater than equal to 0, strictly greater than 0. Or if you want to make it more correct, you can put a mark. Right? There is no number, there's no set of weights such that this quantity holds. Now, if that is true, then this set of constraints, this is like a whole list of them, like one constraint for every training example, has no feasible set. There is no feasible solution. There is no W that satisfies all the constraints, which is a bit of a problem. Because the optimization says, find the W that has the lowest norm that satisfies all the constraints. There is no W that satisfies all the constraints, so this thing crashes. If you want to think of it from a programming point of view, this is where you throw an exception. So basically, hard SVM only works if you have a linearly separable data set. As an aside, by the way, the hard SVM is also a way of detecting whether a data set is linearly separable. If the program crashes, it's not linearly separable. So, it's a constraint optimization problem. If the data set is not separable, there is no W that satisfies all the constraints. This leads to what is called an infeasible problem, and there's no solution, so learning does not work. Of course not, it works because we need to be able to fix it. The crucial idea in fixing this is to say, the data set may not have been linearly separable, but maybe if I delete some examples, if only I could delete some of these bothersome examples, then the data set would have been linearly separable. In this case, there are these two examples. There is the minus, which is clearly in the wrong place, and the plus. It would have been nicer if it was thrown out, that way I would have gotten a larger margin. If I was allowed to arbitrarily delete examples, then I could use the rest of the examples to find a classifier that has a large margin, and life would be good. All I need is some way of detecting which examples to delete. In some sense, these outliers. How do I do that? Let's think about what it means for this example to be on the wrong side of the margin. We wanted y W transpose x to be greater than or equal to 1 for each example. So on this one side, that number is positive. Let's take this example. So for the negative examples, YW transpose X is still positive, right? So this is 1. But it's on the wrong side, so it's 1 minus some slack. Let's correct some slack. Let's allow it to break the margin and go to the wrong side by some amount. Let's cut some slack for this one also. So this is 1, and let's give it this much slack. So we are instead of saying YW transpose X should be more than 1, we demand that I W transpose Xi should be more than 1 minus some slack I. Now this is the Greek letter psi, which I never learned how to write. So I just write a squiggle. So what we want is the separator should be large enough, so provided that we kind of let some examples break into the margins. The way to formalize that is we introduce one slack parameter. That's the correct way of writing psi, if you've not seen it before. There's no way I'm going to learn that. So what you do is for every example, you introduce something called a slack variable. The slack variable associated with an example is basically saying this is how much I'm allowing that example to break into the margin. What does it mean to break into the margin? It means I'm reducing the margin just for that example. All examples have a margin of 1 except for that example which has a margin of 1 minus slack. But what's special about the ith example? Let's do it for all of them. For every example, instead of saying that YW transpose X should be greater than 1, we're going to demand that YW transpose X should be greater than 1 minus psi I. But of course, we want the size to be positive. The slack should be positive, otherwise we're just saying it should be on the correct, it makes things more messy. So the slack should be positive, and we are allowing every example to be more than YW transpose X plus psi I. Now, can someone spot a problem here? Yes?
Would it be for like regular examples?
Sorry?
When computing your the slack for your regular examples, be a problem?
That's one problem, but I'm going to argue that this is a pointless solution. Imagine, so I say that the slacks are numbers that are positive, right? Let's say I set the slack to infinity. I could set the slack to infinity, so that means YW transpose X greater than negative infinity. Of course that's true. I don't need a learning algorithm to find that. So we can't allow the slacks to grow. We can't allow the slacks to become too big. We need to somehow control the slack variables as well. So the intuition here is that the slack variables allow individual examples to break into the margin arbitrarily. If the slack is 0, and this is the case, this is the best case. When the slack is 0, this means the example is correctly classified. It's on the correct side of the margin. It's either on the margin or far away from the margin on the right side. It's one of these good examples. But slack less than 0 means that this is a troublemaker. So what we want is for every example, YW transpose X should be greater than 1 minus the slack, where all the slacks are positive. But at the same time, we don't want the slack to grow too much, so we're going to update our minimization problem. We're going to say that our minimization problem is to minimize the norm of the weights plus the sum of all the slacks. That way the slacks don't grow. That's so really the big change here is that I'm allowing certain examples to break into the margin. And that gives me the flexibility to deal with data sets that are not linearly separable, which is basically every data set out there. So this is called the soft SVM. Actually, it's just called SVM. I call it soft to contrast against hard. When people say support vector machines, this is the optimization problem they are referring to. It consists of it's an optimization problem where the objective for optimization consists of two parts. It consists of the norm of the weight vectors, the half W transpose W, and we know why that's there. Minimizing the norm of the weight vector, maximizing the margin, increase better generalization. There's a second term that says minimize the total slack. Allow as few examples as possible to violate the margin constraint. There is this C that I promised would show up. The C is the trade-off between these two terms. How much do I care about generalization, that's the first term, and overfitting, that's the second term. Because imagine if all the xi's were forced to be 0, we are demanding that the classifier should perfectly classify the training set. If all the xi's are 0, that means we are overfitting the data set. If the W is, so the first term is generalization, it pushes for generalization. And the second term pushes for overfitting. We don't want either of these things to dominate. We don't want overgeneralization, or rather it's called underfitting, because that would basically mean minimizing the norm of W is you get the 0 vector. And the second term is we don't want overfitting because we know about the perils of overfitting. And the objective says we want to balance these two things. We need to somehow balance these two things, and that gives us our one hyperparameter, C. C is the hyperparameter that says how much do you care about overfitting versus underfitting. You want to minimize this quantity such that every example has a score of at least 1 minus its slack, where all the slacks are possible. You can actually eliminate all the slack variables, and that will be the last thing I'll show. You can eliminate all the slack variables because you can, this quantity here, just like you have a term psi greater than 0, you can take this and say psi greater than 1 minus. I've noticed I've cleverly kind of lost the bias term. The bias is always there. So psi is greater than 0 and psi is greater than this quantity, which means it's greater than the max of those two things. And I can replace the objective, I can replace these two together mean psi I is greater than max of that. And now I can replace psi I in the objective with this quantity and get an unconstrained optimization problem that looks like this. I want to minimize over all the W's. Notice that I've lost all the slacks. I have no constraints. I want to minimize over all W's the sum of two things. The first term is the sum of the weight vector, and the second term is this sum over each example of max of 0, 1 minus y w transpose x. And that form is more interpretable. I'm going to take, no, I don't want to take another minute because most of you have other classes. So I'll stop right now, and we'll continue the next lecture where I talk about why this is interpretable, why this leads to this risk minimization principle, and get into how we actually solve the optimization problem. I have office hours at 4 o'clock. Keep it short.
Well done.